Imagine holding a teaspoon of something so heavy that no human machine could lift it. Not a teaspoon of metal, not uranium, not anything that could naturally exist on Earth. A teaspoon of neutron star matter. Depending on exactly what density you assume, popular estimates put its mass at hundreds of millions of tons, and in some comparisons, around 1 billion tons. All inside something small enough to fit on a spoon. And somehow, that is not even the strangest thing about neutron stars. To understand how matter becomes this extreme, we have to watch a massive star die. For millions of years, a massive star survives through a battle between two enormous forces. Gravity tries to crush it inward. Nuclear fusion produces pressure that pushes outward. As long as the star can generate enough energy, those forces remain in balance. But eventually, the fuel changes. The star builds heavier elements. Until an iron-rich core develops, fusion can no longer provide the energy needed to support that core, and suddenly, gravity wins. Until an iron-rich core develops, fusion can no longer provide the energy needed to support that core, and suddenly, gravity wins. Until an iron-rich core develops, fusion can no longer provide the energy needed to support that core, and suddenly, gravity wins. The core collapses. Matter falls inward at extraordinary speed. Under immense pressure, electrons and protons are driven together, producing neutrons and neutrinos. In a fraction of a second, an object larger than Earth can have its core compressed into something roughly the size of a city. The outer layers of the star can then be blasted into space in a supernova explosion. What remains may be a neutron star. And this is where normal intuition becomes almost useless. A typical neutron star can contain more mass than our Sun, inside a sphere only about 20 to 25 kilometers across. Imagine compressing something heavier than the Sun until it could fit inside the boundaries of a major city. No way. The density becomes extraordinary. A cubic centimeter of neutron star material can have a mass of hundreds of millions of tons under representative assumptions. That is why you often hear the famous teaspoon comparison, but it is important to understand what that actually means. A neutron star does not have one perfectly uniform density. Its density changes dramatically from the crust toward the core. A teaspoon also isn't a scientific unit with one universal volume. So claims like a teaspoon weighs exactly 1 billion tons are simplified illustrations, not precise measurements. Depending on the assumed density and spoon volume, estimates can range through hundreds of millions of tons and toward roughly 1 billion tons. The exact number is less important than the scale. A tiny amount of this matter would outweigh mountains. But what could possibly compress matter that much? Gravity. On Earth, atoms are mostly empty space. A tiny nucleus sits at the center, surrounded by an electron cloud. But inside a collapsing stellar core, gravity becomes so intense that ordinary atomic structure cannot survive in the same way. Matter is forced into an extreme state dominated largely by neutrons. And even then, the collapse has to stop. Quantum physics provides part of the resistance, preventing the neutrons from simply occupying identical states. While the strong nuclear interaction becomes crucial at these densities. The result is one of the densest forms of stable matter known to exist. Go much further, and even a neutron star may lose the battle. If the collapsing core is massive enough, no known pressure can stop gravity. A black hole can form. That means a neutron star exists near one of nature's most terrifying boundaries. Dense enough to crush atoms, but not quite dense enough to disappear behind an event horizon. And gravity on its surface would be almost impossible to comprehend. If you could somehow stand there, which you absolutely could not, you would experience gravitational acceleration billions of times stronger than Earth's. Dropping an object would not look like dropping something here. It would be violently accelerated toward the surface. But neutron stars have another trick. They spin. Some rotate dozens or even hundreds of times every second. Imagine an object heavier than the sun, the size of a city, completing hundreds of rotations every second. Some neutron stars produce beams of electromagnetic radiation from regions near their magnetic poles. If those beams sweep across Earth as the star rotates, telescopes detect extremely regular pulses. We call these objects pulsars. When pulsars were first discovered in 1967, their signals were so regular that researchers briefly considered whether an artificial source needed to be ruled out. The explanation turned out to be even stranger. The universe had created a cosmic lighthouse. And then there are the magnetic fields. Some neutron stars, called magnetars, possess the strongest magnetic fields known in the universe. Fields trillions of times stronger than Earth's magnetic field. Under conditions this extreme, matter and radiation can behave in ways we cannot reproduce on Earth at comparable scales. That is why neutron stars are so scientifically valuable. They are natural laboratories. Places where gravity, nuclear physics, quantum mechanics, and electromagnetism collide under conditions no human experiment can fully recreate. And we still do not know exactly what exists deep inside them. Are their cores mostly neutrons? Do exotic particles appear? Could matter transition into states involving deconfined quarks? Scientists are using gravitational waves, X-ray observations, pulsar timing, and other measurements to narrow down the possibilities. But the deepest interior remains an active frontier. Maybe that is the biggest WTF moment. We can calculate the motion of planets billions of kilometers away. We can detect galaxies from the early universe. Yet inside an object only the size of a city, nature can still create matter we do not completely understand. And objects like this are not hypothetical. They exist, right now. Somewhere in our galaxy, city-sized remnants of dead stars are spinning through darkness, with more mass than the sun compressed inside them. Meanwhile, here on Earth, we make coffee, answer messages, complain about traffic, and live ordinary lives in the same universe that can create something this extreme. If this made the universe feel more terrifying and more incredible, subscribe. Every single day, we uncover another hidden truth about reality, science, space, and the human mind. Because reality doesn't need science fiction to become unbelievable. Sometimes all we have to do is look at what actually exists.